Majority of the topics in linear algebra is going to be centered around two main operations, and those two operations are vector additions, which is adding two or more vectors together to create a resultant vector. So that's one of the main operations that you will be coming across. And the second operation that is also important for you to understand is the vector multiplication operator. So let's go and carry out a simple illustrative example of how the vector addition is done, both in geometric sense and also in the numerical sense. So let's say we have a vector v, which is defined by this red arrow geometrically, and if you take another vector, which is w, which is defined by this yellow vector. So what does it mean to add these two vectors together? So let's first of all have a geometric understanding of what it is meant, and that will help us also in numerically implementing, or also in the numerical way of doing the vector addition. Okay, so we want to do this operation, and in order for us to do this operation, what is essentially done geometrically is you will initially have the v vector, which is the starting vector. Then what you will do, you will take this w vector and you will translate this w vector to the tip of the v vector. So if I do that, then this translation will essentially shift this w vector to the tip of the v vector, and then we will arrive at new tip. Now taking the origin and connecting this new tip is going to be the resultant sum v vector plus w vector. So this vector yellow described in here, this slide, v plus w is essentially going to be the resultant, and this is like the vector addition, simple vector addition in two-dimensional geometric sense. Okay, so if we take same thing, right, which is this, let's see how do we numerically implement this, right? So if we take the red vector and let's say this vector is defined by this order list in square bracket by 3, 4, right? That's the representation, numerical representation of the red vector or vector v, and then we have this sort of yellowish vector where we have the numerical representation 2 minus 1, right, in square bracket, which is the order list, which is a way to represent a vector numerically. And if I want to sum them up, then the simplest way to do that numerically is if you have vectors x1 and y1, which is first vector, and if you have the second vector, which is x2 and y2, right, then the vector addition, let's say I'm just using this v and w. If I want to find out what v plus w is, essentially in simple terms that will be x1 plus x2. So you take the first component in the order list and you sum them together. So you create sum here, and you then take the second component in the order list y1 plus y2 and you sum that together, and this becomes your essentially the resultant vector. Okay, so let's take the same example that we are running through. This was like the first vector, right? And then what we want to do is we want to find out where it goes, right? So if once we added this, right, we move to a new location, which is given by 5, 3. Okay, and as you will see, when we are implementing this whole thing numerically, which is basically adding this 3 plus 2, will arrive at 5, and then 4 plus minus 1, that will arrive at 3. So this is like so the correspondence between the vector addition in the case of geometrical sense and also in the numerical implementation sense too. So let's take a look, how do we arrive at this 5 and 3 in geometrical sense, right? So what we are doing is, first of all, we are taking the first component of this red vector, which is 3, which is telling us to move 3 units in x direction. So that's what we have done. And then we will take the first component of the second vector and we will move 2 units more. So this is what we will do. And so if we move 2 units, the resultant 3 plus 2 is 5, and that's why we have 5 as the first element of the vector representing this yellow. And similarly, if I take the y component or the second component of the order list, first that we need to do is we need to move 4 units positive in y direction, and then the The second thing that we will need moving is 1 unit backwards, like or negative y direction. So I moved here and then moved back here, and that resulted in 3. And this is another way to understand or at least understand the concept of matrix addition geometrically. Okay. The second important concept that is required for us to understand is of the concept of scalar multiplication. So you take a number, or what we call you take a scalar and you multiply that to the vector. And here in this notation, essentially, or sometimes scalar and numbers is used interchangeably when we are talking about the scalar multiplication. Essentially, scalar multiplication is multiplication of a vector by a given number. Okay? And that's what we will be focusing on. And that's an important operation that we need to be understanding, and it has various different applications. Let's move on to the second important vector operations, which is known as scalar multiplication. And essentially, it entails multiplying a given vector by a scalar quantity or a single number. And in that setting, essentially the scalar and the number terms are used interchangeably. And scalar multiplication of a vector is essentially multiplying a vector by a given number. Yep. So if I take an example, and let's see what it means geometrically. So if I take this example, and we have a vector which is listed here in the red, and if I multiply this with a quantity 2 or a number 2, what does it mean? It essentially means changing the length of this, or the magnitude of this vector twice the original magnitude without affecting or changing the direction. Okay, and that's what we have. Basically, the number multiplies the magnitude, but it does not affect the direction, and that's an important concept. So when you're multiplying a vector by a number, you are only changing its magnitude, but you are not doing anything to its direction per se. So if I take a number 2 and multiply that by a vector 2, then essentially what is going to happen, this vector is going to stretch, and it will become twice the size of the original vector v, but the direction, which is general direction here, is not going to change for this vector we have here. So this is essentially a scalar multiplication operation that happens with respect to the vectors. Yep. Again, if you do different multiply by different numbers, then this process will be stretching, squishing, or reversing. And so if you multiply this vector by a negative number, then it will be reversing its direction. Okay? If you multiply this vector by a smaller number than 1, then essentially this will be squishing and making this vector smaller. Whereas if you are using a number higher than 1, then you are essentially stretching that vector here. And those are the different operations that you can do with respect to the scalar multiplication in the vector domain. So let's take an example problem, and we will try to go through this again. So here we have a vector, and then we multiply this vector by this magnitude minus 0.50. So if you do that, what essentially it entails is taking this minus 0.5 and multiplying that by 4. That will result in minus 2. Taking this minus 0.5, multiplying that by 2, that will result in minus 1. Okay? And this is how the scalar multiplication is implemented numerically. You take the magnitude of the scale and multiply that with the individual element of the vectors, and whatever is the resultant quantity is going to give you the location, or what is the vector after the scaling effect, or after the multiplication of a number by that vector itself. So if you do that, we will see this number is minus 2 minus 1, and if I create a vector which represents minus 2 minus 1, this vector will be represented by this one. As you can see, what this has done essentially, it has reversed the direction of the original vector, and then it has squished this vector by half of its original magnitude. So this is the geometrical interpretation of this vector multiplication aspect, or scalar multiplication of vector, that we see here.